In this video, we're going to talk about linked lists. In particular, it's going to be an introduction to the concept of a linked list. So the textbook does a fair job of explaining all this, but I'm just going about it a different way. There'll be other videos on linked lists to talk about how to manipulate them, but I think the conceptual overview with just a touch of code is the way to start. So the first question you may be asking yourself is, why do we need linked lists? We saw it in the first C++ class that having a data structure, the array is the one that we used, is pretty useful. That way you don't need a separate variable for everything that you need. So if you have, you know, a classroom maintenance program with 50 students, you can have an array of students with one name and different locations rather than a bunch of random names that are hard to maintain and you can't iterate through. Okay, so arrays are great. So we're going to look at how arrays work a little bit. So what I've got here on the screen now, I'm just doing this in Google Sheets, which is, like Excel. So basically, it's just a memory map that I've created. These numbers are totally made up. But as you can see, hopefully you can recognize. If not, you will get it in some class. Binary numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then the same way down here, except we have 11 and 12. Okay. And basically the way this memory map works, this visual aid that I'm using, if we have X here, we create an int X. Okay, so I guess we would have some code over here. If we do an int X, semicolon, and because of OCD, make the font correct. Okay, then it would create, and I'm assuming here that these blocks are the size to store an integer. Okay, which is 8 bytes. I want to say, I forget. It doesn't matter. You can look it up if you need it. But C++ in every language will determine how big an integer is. C++ does have short ints and long ints and long ints and all that. But these are just basic ints. So memory itself will be divided up bit by bit by bit. So in this totally made up scheme I'm doing here, we're making a lot of assumptions. But the assumption is each box is the size of an integer, can hold one integer. Okay. So we store that, we say int x, then the computer will randomly, and right now the blue means empty, so everything is empty. Okay, so we're going to store, the pink shows that it's stored. We've stored the value x. Okay, that's not what I want to be doing. Let's do something real. I love when my examples are only semi thought out. Int x is equal to, let's say, 6. Okay. It's the 6 that gets stored here. Okay. So what is X? X then is a shortcut to get us to this memory location. Okay. X is not a pointer per se. It's more like a name of what's at that location. So a pointer would return the 0011. And I am being Mr. Typo today, to no one's surprise. 0011100100. That's what we would return if the integer X was a pointer. So it's not. Okay. So X is stored at, okay. So the location of X then. Okay. So the ampersand X then would be equal to that memory address. Okay. Anyway, so that's all we've done. Okay. So to get the nomenclature down here. So now let's say again, each block is holding an int, and we're going to create an array. Okay, int a bracket 5. The bracket 5 means it's an array. Okay, so this gives us 1, 2, 3, 4, 5. Okay, so one of the problems that we have with arrays is one of the efficiency of memory. We're lucky most of the computer systems that we're on, at least when we're in school, have what seems like unlimited memory. They don't really, but it's a lot bigger than we need. So we don't become miserly with our memory. The first computer I ever owned had 16K of memory. K is in 1,000 bytes. And we had to be super concerned with memory. But there's still an area where memory is a factor, and that's in embedded systems. Little tiny chips that work, in your car and your refrigerator and your microwave, things like that. So when you're programming for those chips, you do have to be careful of memory. And it's certainly the case that wasting memory is never a good idea. Okay. But if you have, so I guess this leads to the second problem with arrays. So arrays have to be contiguous memory. So if you have a situation where you're going to do students in a classroom, okay, and you have no idea how many students there are going to be. So what do you do? Say, oh, let's make the array size 100, because that way we'll be sure to have enough. Okay. But when you do that, you have blocked off 100 consecutive integer size blocks of memory. And if you don't need that many, it's wasted memory. So that's a problem. You may be thinking, well, can't we do dynamic variables if we don't know? Well, we can, but we're then just deferring it. And there's a technical answer that we'll talk about when you take operating systems. You're referring it to a different part of memory, but you still have to tell it at the time you create the array how big it's going to be. So you've moved it from compile time to runtime, but you still haven't solved the problem that you have to take up one big chunk of memory. And that can be a problem. Okay. There are some advantages that come with this array, namely being that you have direct access to every single element of the array. Okay. And if you think about arrays, and we talked about arrays before in a previous class, array is just a pointer, really. It's a pointer to a memory address. Okay. So when we do something like A0, what that's really saying is go to the 00100010 and don't add anything else. Okay. That's why we start with 0. When we say A sub 1, it's saying go to 00100010 and add one integer size, add the size of an integer to get us up to this next block. That's where that comes from. Okay. So we can get directly to the fourth element, or if it's 100, the 99th element, the 100th element, the 48th, whatever, we can skip around. So we have direct access, which is good. Okay. So the cons of arrays, you have to know how big they're going to be before you start. They have to be in contiguous memory, and they can be wasteful because of that. But the advantages are, the pros are that you have direct access to every element and you can iterate through it pretty simply. Okay. So in an environment where memory matters, and C++ was developed a long time ago, but even now, performance matters. And the more efficient you are with memory, typically the faster your program's going to operate. There was this idea of what can we do to make this more efficient. Okay. One of the ways, so this whole class is about ways to do that. So one of the ways that we can do that is if we can find a way, instead of having to allocate an entire block of memory, what if we could only do one? Okay, so what if we could, here we have our first memory. Okay, we know we need one, we create one. Okay, so now let's say we want to create another one. Okay, and it could be right next to it, but if we knew that was going to be the case, it wouldn't be an issue. So if the memory were used a lot, okay, then maybe we put it here. Okay, and one thing I didn't say before, at least I don't think I did, but just to be clear, these memory addresses are determined by the operating system using some kind of a formula that we'll talk about in operating systems class. Okay, so for us, it's random, at least acts like it's random. Okay, so if it puts it here, you can say, well, great. Now I need to and I have to. Okay, the problem is though that unless you're going to create two separate variables, which becomes a problem ramping up, like when you have 100 students and you need a variable for each one. So the data structure has to connect them in some way. If we were in contiguous memory, we would know, okay, I'm at the first student. Where do I go to the next one? I just go to the next block of memory, move over the size of an integer or the size of a record. There I am. Okay. But we don't know that here. So to create this next data structure, the linked list, we're calling it, we have to add a pointer to be taken along with the integer that we're wanting to store. We're doing integers, but we can do anything. Okay. this pointer has to point to the next one. So I think of this kind of like a treasure map, okay, where you have a bunch of steps that you have to follow. Okay, so if this is our first node and we're here, and there's whatever, there's a 3 here, okay, we can read this 3. There's a pointer to this memory, but now we have to say, well, how do I get to the next one? Well, we have to add something else. So we have to add a pointer here that will point us from here down to this one. Okay, let's say there's a 7 there. Okay, and further, there could be one down here, could be anywhere, could be over there in case memory gets reused later. Okay, so let me make this one show as being used. Could be over here. Okay, so this one would say, oh, okay, go here next. This one would say, go here next. Okay, so that's the basic way these work. So they link together. Okay, the last in the linked list should point to null so we know we're at the end. Okay, so, and there's a lot more to it. We'll see some of this in the code, but the advantage to this is we only use as much memory as we need. The memory that we need can be placed wherever it needs to be. Okay, there's a problem called fragmentation that if you have enough memory available to put your array in, but you don't have it together in one big chunk, then that's a problem. It's not gonna work. Okay, so this is very efficient with memory. If you have 10 blocks available in memory, no matter where they're located, then you're able to store something that takes a size 10 of that size block. Okay, so those are the advantages to them. So we're going to have to go through some logic to figure out how to populate, how to maintain, how to deal with these kinds of data structures. But that's the overall idea. Okay, and the book has some ways to draw some graphs and things like that. And if you've had me, you'll know that I've said since almost the first day of class, if not the first day of class, that you have to know what you're going to program before you can start typing it. And we really are past the point of being able to type things in. Okay, particularly with these data structures we're going to be talking about in here, the linked lists, the stacks, the queues, the trees. We need oftentimes to make a diagram where we can map out step by step what our code's going to do. Okay, so let's actually look at some code here of a fairly straightforward example. Okay, so there are lots of complexities and lots of options, maybe not complexities, lots of options when dealing with linked lists. Okay, so the most basic choice that we're going to make, and the book makes the same thing, the same choice, but we could do other options, is that we're going to define our node as a struct. Okay, so a struct, basically the way we use them, everything's public and it doesn't have any functions. Okay, it only has member data. It turns out, and I was surprised to learn this shockingly recently, that we could add functions and everything else to structs. We can treat them just like classes, but we don't. There's no need to do it. So a struct, we're going to say, for our uses, can only contain member data, and that's it. Okay, so I've got a struct called node type. Again, I could have made that a class. I could have made the linked list a class. We have lots of options, but for now we're keeping it simple. Okay. It's also important at some point we're going to start templating these so it can hold not just an int, but hold whatever type we want. Okay. Not, it's all the same type for one list, but the same code could create a list of doubles or a list of ints or a list of strings. Okay. So in our struct up here, we're just going to call it node type. And it's going to have the two things that we need. It's going to have an int. In this case, this is of a type int. So whatever the type is, called info. That's where we're going to actually store our data. Okay. Then we have to have a link, which is a pointer to another node type that's going to store wherever the next link in line is. Okay. So creating the first one's pretty straightforward, but there are some steps here that we have to think about. So first we have to allocate some memory for this new node. Okay. So to do that, we have to create some node type variables. Okay, node type pointer variables. Okay, so I've got here node type. Again, that's what I called this up here. This is not special. You could call this puppies if you like. Not that it would make any sense. So we have our node type here. We have a pointer to a node type called head. We'll talk about head in a minute. We don't want to lose our head. And then we have this pointer called new node. Okay. So the basic idea on this linked list, we're going to create the first node. We're going to put info in it. We're going to point the head pointer to this new node. We're then going to create a new node that'll allocate new memory, but we've saved the other value as head. Okay. We'll keep adding it in that way. That takes a little while to feel comfortable, but that's the basic idea. Okay. So we're now going to create this first node that has its info of 5. Okay. So I'm going to say new node is equal to new node type. Pretty basic. Okay. I'm going to say that the new node type info. So this may be a new operator for us. Okay. This is a dash greater than. And this allows us to get to information stored inside of another structure. Okay. So the new node arrow, I guess, which is the dash greater than info, we're setting it equal to 5. Okay. And since this is our first node and we don't know where we're going to go with it, we're going to set our new node link equal to null pointer, the nullptr. It just points to nothing. Okay. So we're now going to set the head of our new list. So in this case, our list is going to be called head, I guess. It doesn't really have a name. It's all just memory module or memory pieces put together. So we're going to say head is going to point to this first new node that we have created. Okay. So now that we've done that, head arrow info is going to be equal to 5. And head arrow link is going to be equal to null right now. Okay. So we can create at this next line another new node type. Okay. So if we didn't set this to head, this would have wiped out the first one because they'd have had the same memory address. But remember, the new keyword allocates new memory. So now we have memory that we can put new information at. So just like above, we're going to set the new node info equal to 50 this time. And again, our new node link is equal to null. Okay, the null pointer. Okay. So our original new node is gone. Well, it head points to that. We're creating a new node. We now want to connect these up. So we want the new node, the new node, okay, to be connected to our original node, which head points to. Okay. So we can do that in this way. Okay. So head points to our original node. Okay. So head link, which we had set the first time back up here to null pointer, is now going to be equal to this new node that we just created. Okay. The one that has 50 in it. Okay. So our link is there. So we're good. Okay. So now if we want to get to the data, okay, so if we were to print out head info, okay, let me just make a little note here in the comments. With what we have, head info is equal to 5. That's our original array. Okay. Head link info is equal to 50. Okay, that says go to the head node, first node we created, follow the link that gets us to the second node we've created, and read its info. Its info is 50. Okay. So we could do things this way, but this is going to become very cumbersome very quickly. Okay. So we don't want to do that. So what we're going to have to do, and we can't ever change root. We can't just say root, we can't, if we want to iterate through a list, and the book has some good illustrations of this. Okay. But if we have a list of 10 nodes, if we were at the first node, so we're at head, we could make head point to the next node by saying head is equal to head link. But when we do that, we've now changed head and we can't go back anymore. So instead, we're going to create a pointer, basically. Not that sounds more complicated. We're going to create a pointer and set it initially equal to head. And now we can iterate and change it to point to all the nodes. Okay, I think that's an easy way to do it. And I've got this as a separate line here for the P. But really, it makes more sense, I think, code-wise, just to go ahead and put this up at the top with the others. Okay. And when you find yourself needing another variable to declare, just go back up to the top and do it. I wouldn't try to get them all before you get going. Sometimes people do that. It gets confusing to them. Okay. So now that I've got that, I can set the initial value of P by saying P is equal to head. Okay. So P points to the head node. Okay. So if at this point I would just say print out P info, it would be 5. Okay. But what I can do, I can go through a loop here. Okay. I can do a loop here. I can say while P, and this is saying while P is not null. Okay. So while P has a value, I'm going to see out its info. Okay. So the first time this happens, I'm pointing to the original node. Okay. So let's actually flip back over just to make sure we're seeing this a little bit better. I wish I could just, draw on the screen, but I don't have those current capabilities where I'm at. Okay, so let's say instead we have, just move this one over. We only have 2. Okay, so head points here. We'll just make that little note there. Head points there. Okay. So if we were to say P is equal to head, okay, now both P and head point here. Okay. So the first time through this loop, we're going to print out P info. It's going to print out that should be that's a 5, and that's a 50. It's going to print out a 5 that first time. Okay. Then so that's the P info is equal to 5. Then if I were to say P is equal to P link, okay, it's going to move P from here to whatever the P link is, which is this one. So P now points here. Okay. So now when I print out the P info is equal to 50. Okay. Now when I say P is equal to P link again, the link for this node is a null. So now we're at null and we break out of our loop. Okay. Matters not where these things are located in memory for this to work. Okay, so let's go back to the code here. So that's what we're doing here. So first time through, this is equal to the 5. We're going to do P equal P link that moves to our second node that we've created. Okay. Prints out, goes back around. It's still not null. Prints out the 50. It sends it to the third node. Okay. Which now is null. So when it comes back again, that's not true. And we exit. Okay. So that's the basic way this is going to work. Okay. So we can create another node if we want. Okay. As long as we keep adding it to the end. Now, when it comes to adding new nodes, we have to think about what we're doing. Okay. We're going to have to create a new pointer. We have to follow the existing linked list to the end if we want to add it to the end. Okay. It's also possible to add a new link to the beginning of a list or to add one somewhere in the middle. Okay. So that's beyond the scope of this particular video, but it is in the book and it's worth looking through. There'll be other videos that give us more of an example here. Okay. So again, to reiterate, we're going to create a struct. Could be a class. We're making the choice for it to be a struct. We could create a class for our linked list in general. We're not doing that yet. So the struct just has info. It has link. Sometimes this is called data instead of info. It could be called other things besides link, but these work too. Okay. We have to declare a node type pointer before we create our new node, and then one for head. And then we use the new keyword to create the node type. We use the dash greater than nomenclature to get to the info and the link inside of our struct. Okay. And then we set the head to our first node. We add whatever nodes that we want, and we're just adding one at the end because we can do this pretty easy. Okay. And then we can go through like this in order to print out and iterate through the list, no matter how big it is. Okay. So make sure that this makes sense before you move on to the rest of the book and the other videos. Linked lists can confuse you. You can think you've got it, and then you'll just lose it. And that's just part of the game. Okay. But again, make pictures, draw on paper. Make sure you've got a legal pad and some pencils. It's a very powerful programming tool. Okay, so until the next video, keep working on the list, and we'll go from there.